Hi everyone. In the last class, we have discussed about the Gleason-Kahane-Glasgow theorem. So let us quickly recall. Let A be a unital Banach algebra and phi be a linear functional on A. Then we have shown that phi is in MA, that is, it is multiplicative if and only if phi of 1 is 1 and phi of A is non-zero for every A in G, the set of all invertible elements of A. Okay. Now let us look at the set MA. So we can say what kind of properties the set MA can have. And what are the advantages having this set? What is it useful to describe the algebra? Soon we are going to discuss that if you have any commutative unital Banach algebra, that can be seen as a subalgebra of C of MA. So that is a Gelfand theorem. So before discussing that result, we need to study some important properties of MA. The question we can ask is that is MA empty? Is MA non-empty? If it is non-empty, what can be said about MA? This is the question we can ask. So in general, MA may be empty set. We have seen set of all 2 by 2 matrices. It doesn't have any maximal ideals, hence it cannot have any multiplicative linear functional on that. But when A is commutative, so let A be a commutative unital Banach algebra, and if you take any element in A which is not invertible, then we can show that then there exists a maximal ideal I containing A. So we have seen that if A is a commutative unital Banach algebra, there is a one-to-one correspondence between maximal ideals and the multiplicative linear functionals on the algebra A. Now using that we can actually prove the following this result, that given any non-invertible element, we can find an ideal containing that element, and by using Jones' lemma we can conclude that there exists a maximal ideal containing the given element. Okay, that means once there is a maximal ideal, by the earlier result that we have proved, we can find a multiplicative linear functional on that. That means in this case, from this we can actually show that if A is unital commutative Banach algebra. Okay. Now we want to show that With respect to some topology, MA is a compact set. So the goal for today is MA is compact in the weak star topology of A star, where A is the dual of A. So let us quickly discuss about weak star topologies. Before discussing weak star topologies, we need to discuss about weak topologies. So next we discuss about okay. Suppose X is an unempty set and X alpha, tau alpha. This is a family of topological spaces. Now let us look at this collection of functions f alpha coming from f alpha defined on X and taking values in X alpha, tau alpha. This is a collection of functions. We can ask the following question. Question is, find a topology tau on X such that f alpha is continuous on X tau for each alpha in. So in this case the answer is very simple. You take tau to be the discrete topology. But this is a trivial topology. We want a weaker topology, a smallest topology, which make each f alpha to be continuous on X. So we can modify this question. Find the smallest topology on X such that each f alpha is continuous on X. So let me call this is tau. Okay, so let us see what is the way to construct such a topology. So suppose we have such a topology. We want to look at f alpha inverse u alpha, where u alpha coming from the topology tau alpha. Now they are all inverse images of open sets in the space X alpha. So let us call this as the set S. If there is a topology on X such that each f alpha is continuous with respect to that topology, then this collection should be inside that topology. That means we need a smallest topology which contains this collection. So the smallest, so what we require is the following. So need to find the smallest topology on X containing the collection yes, or the smallest topology generated by S, or the smallest, the topology generated by S. How it look like? So in this topology, a set U is open if and only for every x in U there exists alpha 1, alpha 2, alpha n coming from this set lambda such that X is in F alpha 1 inverse U1 intersection F alpha 2 inverse U2 F alpha n inverse U. Or we can say that F of F suffix alpha j X is in Uj. Okay, so this is a topology. Once we have a collection, we can find a topology generated by that collection. So that is the smallest topology. So this is a required topology. Let us make a particular case. Take X alpha equal to R or C with the usual topology. Then this collection F is nothing but set of all functions F from X to R. So family of functions. Now in this case, so let us take epsilon positive. Then we need this collection S as F inverse of, so here we can take F alpha inverse minus epsilon comma epsilon, where epsilon is positive. So U is open in X with respect to this is with the weaker topology, if and only for every X in U there exists alpha 1 so on alpha n in lambda such that mod F alpha j X is less than R. Okay. So this topology, whatever we have discussed, is called the weakest topology or the weak topology generated by the family of functions F. So we can write here, so the sigma X F, the weak topology generated by the family of functions F. Now in this particular case, here also the weak topology generated by family of function is generated by sigma xf. Let us look at a few examples to understand this point. So let us take xt to be a metric space. Let xt be a metric space. Okay, let us take u in X. So define a function f suffix u from X into say R by fu at X is distance between X and U for every X in X. Now let us take this f suffix u is coming from X. Now look at the weak topology generated by F or the smallest topology generated by F, which makes every fu continuous. Now how a sub basic open set look like? Let us look at so let us take fu inverse of minus r comma r. So let us start with some positive number r. Then this is nothing but, so we are looking at fu inverse of open sets on the right hand side with respect to the usual topology. It is of the form minus r comma r. So this is set of all x such that fu of x is in this interval. So this is nothing but set of all x in X such that d of x and u or ux is less than r. And this is nothing but the ball centered at u with radius r. Of course, in the complex field, you will get, if instead of r, if you take c, then you will get ball centered at u with radius r. Otherwise, we will get the interval minus r comma r. Now that means the topology generated by these balls centered at various points is nothing but the metric topology. So sigma x f in this case is the metric topology, which is generated by balls of this kind. Okay, let us look at one more example. So let us take x alpha, tau alpha be a family of topological spaces. Let us take x to be the product space. So this is nothing but set of all functions x such that whose domain is lambda and taking values in union x alpha such that x alpha is exactly in x alpha for every alpha in lambda. So such a function exists by the axiom of choice. So this set is non-empty by the axiom of choice. Okay. Now let us look at define p alpha from x to x alpha by p alpha. So here every element is of this form x alpha. Now you send it to x alpha for every. So this is called a projection onto x alpha. Now collect all these projections, this family of functions from alpha is coming from lambda. Now the topology generated by weak topology generated by this family of functions on this on the space x is nothing but it is the topology generated by the collection p alpha inverse u alpha, where alpha is coming from lambda. But we know that this is nothing but the product topology. So this is exactly the product topology on x. So in this case, the weak topology generated by family of projections is the product topology. Now let us make another particular case. Let x be a nonlinear space. Then we know that x star is the dual of x, that is set of all functionals from x into c such that f is linear, unbounded or continuous. Okay. Now let us try to look at the weak topology generated by x star on x. So that is sigma x star is the weak topology on x generated by x star. We know that every functional on x, when f is in x star, then f is bounded with respect to the norm topology of x. Now we are looking at weakest topology on x such that each of these functional is continuous. Okay, so this is a weak topology on X generated by X star. So by using Harmonic theorem, we can easily show that this topology is Hausdorff. So that is, if you take two elements x1, x2 in X, with x1 not equal to x2, then there exists f in X star such that f of x1 is not equal to f of x2. Now from this we can conclude that this topology is Hausdorff. With the more information about sub-basic open sets as well as basic open sets. So sub-basic open set in this topology is of the form. So let us denote by V x naught f epsilon. It is set of all x in X such that mod f of x minus f of x naught is less than epsilon. This epsilon is called the radius of the ball, open ball centered at x naught with radius epsilon. This is open ball or open set, we can call. This is the center. Okay, and sub-basic open sets are of this form. Then we can get the basic open sets, which are finite intersection of sub-basic open sets. So basic open sets, so they are of the following. So B x naught f1 f2 so on fn epsilon. So here x naught is an element of X, f1 f2 so on, fn's are functionals on X, boundary linear functionals, and epsilon is positive. So this is nothing but set of all x in X such that mod fjx minus fjx naught less than epsilon for j equal to 1 to n. And here this is true for all possible choices and choices of functionals, and epsilon is bigger than 0. Okay, now using this definition of sub-basic open set and basic open sets, and using the Harmonic theorem that we have stated in the first statement, we can conclude that the sigma x star is Hausdorff space. Okay, now if you have a sequence xn, so let us take xn to be a sequence in X and x is in X. Then we can say that the sequence xn converges to X in the weak topology sigma x star if and only f of xn converges to f of x for every f in X star. So this can be easily shown using the definition of convergence and by the open sets that we have discussed earlier. Similarly, if x alpha is a net in X and x is in X, then we can say that x alpha converges to X in this topology if and only if f of x alpha converges to f of x for every x in X star. When x is infinite dimensional, we can show that if x is infinite dimensional, so we can show that sigma x star is weaker than and the norm topology of X. Okay. When X is finite dimensional, we can say that both topologies coincide. And one more important property is that when X is infinite dimensional, we can conclude that weakly open sets are unbounded, whereas open sets in the norm topology may be bounded. For example, if you look at the open unit ball in X, that is bounded, whereas if you take any open set in the weak topology, that has to be unbounded. Okay, so this is information about X. Now let us look at weak topology on X star. So here we have the space X star, when X is a nonlinear space. Now sigma X double star, this is the weak topology on X star generated by X double star. So this is a similar topology, same topology that we have discussed earlier. Now we are interested in a smaller topology than this one. For example, we can so we can easily check the following. If F1 and F2 are families of functions on X, then we can show that sigma X F1 is weaker than sigma X F2 if F1 is contained in F2. The topology generated on X by F1 is weaker than the topology generated by F2 on X. Now with the same observation, we can actually look at a weaker topology on X star. So let us look at the canonical map. So look at J from X to X double star. Here J X is a nonlinear space and X double star is the double dual of X. So define by Jx is Ex for every X in X. So where Ex is the evaluation map, Ex is a functional on X star defined by Ex at any functional is f of X for every f in X star. Earlier we have shown that norm Ex is exactly norm X by a consequence of Karman theorem. So this is we have already shown. Okay, that means so we have norm of Jx is exactly norm Ex, that is norm X. Okay, so that means we can say that J is an isometry. It is easy to check that J is linear. Okay, so now we can consider J from X to Jx, the image of X under J. Now this is subset of X double star, X going to Ex. Now this is a one-to-one onto map from X onto J of X. So we can identify X with J of X, and J of X is subspace of X double star. Now J of X is a smaller family than X double star. So it will be same when X is reflexive, but in general J of X is a subset of X double star. Now look at the topology. Sigma X star Jx. So this is weaker than So this is, then this is weaker than sigma x star x double star. That means weaker than the weak topology on x star generated by x double star. So this topology is called as weak star topology on x star. So sigma x star g of x, this is the weak star topology or double star topology on x star. It is generated by g of x. So since x and g of x are same, in the sense that there is isometric isomorphism from x onto gx, we can treat this as the topology generated by x on x star. So here x means g of x. Elements of x we can write as e suffix x, where x is coming from x. So in this topology, so this is weaker than the weak topology in x star, which we call as the weak star topology. Now applying the earlier definition, we can say that x alpha converges to, if you take family of functions, so let f alpha be a net of elements from x star such, and f is in x star, then we can say that f alpha converges to f, the weak star topology. So this weak star topology, if and only if ex f alpha converges to exf for every x in x. So this is nothing but f alpha x converges to f of x for every x in x. Okay. So this is a convergence with respect to the weak star topology. Now we can ask what is the advantage of having this weak star topology instead of considering the weak topology. We are looking at weak star topology. So we know that if you look at the B x star, the closed unit ball in x star, that is set of all f in x star such that norm of f is less than or equal to 1. This is closed unit ball. This is not compact in the norm topology. So this is not compact in x star. So this is when x is finite, x star is finite, infinite dimension. So this will be compact when x star is finite dimensional, but that is with respect to the topology of x star, that is norm topology of x star. But if you look at the weak star topology, we can say that this closed unit ball is compact with respect to the weak star topology. That is called the Banach-Allegro theorem. It says that B of x star is compact with respect to the weak star topology on x star. So this is one of the important results in analysis, where we can get the compactness when we weaken the topology. Okay, so this result we will be using for our representation of commutative C star algebras and Banach algebras at a later stage. So next, let us come back to Banach algebras. Let A be unital commutative Banach algebra. And we know that MA is non-empty, then we can say that MA is a weak star compact. Sometimes we write this double star compact. This is weak star compact in A star. Now we know that MA is a subset of set of all F in A star from F less than or equal to 1, the unit ball. Now we know that this closed unit ball is weak star compact. So to prove this result, it is enough to show that MA is closed with respect to this weak star topology. So claim MA is closed in B A star, the ball, with respect to sigma x star x. So here x is nothing but A, so we can write this is sigma A star A. Okay. Now let us take a net of elements from MA such that phi alpha converges to phi in this closed unit ball with respect to this topology, weak star topology. That means we know that phi alpha of A converges to phi of A, because we have seen earlier that F alpha converges to F in the weak star topology if and only if it is pointwise convergence at every point of this space. Now this implies phi of AB is limit alpha phi alpha AB. This is limit alpha phi alpha A, because these are multiplicative linear functionals. So this is nothing but phi A phi B. So from this we can say that phi is multiplicative, but we also have to show that phi is non-zero. So as phi alpha 1 is mapped to phi of 1 and each phi alpha is 1. Phi alpha 1 at 1 is 1. So hence from this we can say that this is 1. So therefore phi is non-zero. So from this we can say that MA is a closed set in the closed unit ball of A star with respect to the weak star topology. Now since it is closed, and we know by the Banach-Alaoglu theorem that the closed unit ball in A star is weak star compact, we can also say that MA is weak star compact. Okay. Next we define the Gelfand map. So let us take at A be a unital Banach algebra. So we define gamma from A into the continuous functions on MA by gamma A. Gamma A is a continuous function on MA. MA is set of all multiplicative linear functional. Gamma A at phi is nothing but phi of A for every phi in MA. Now it depends whether A is commutative or not. When A is not commutative, there is no guarantee that MA is non-zero. MA is non-empty. But when A is commutative, we can always say that MA is non-empty. So A is commutative. So from now onwards, we assume that A to be commutative. Assume that A is commutative. So this map we call as the Gelfand map. R transformation. Okay. Now what are the properties of this Gelfand map? So one easy observation is that gamma 1 at A, gamma 1 at phi is nothing but phi of 1. This is 1 for all phi in MA. So it sends 1 into the constant function 1. So one of the unit of the Banach algebra is mapped to 1, where 1 is a continuous function, at t is 1, the constant 1 for all. So here phi for all phi in MA. Okay, this is the first. So let us look at AB. So gamma AB at phi is phi of AB. This is phi A, phi B, because phi is multiplicative for all phi is in MA. So this is nothing but gamma A acting on phi, gamma B acting on phi. Gamma A and gamma B are continuous functions, and there the multiplication is pointwise, so we can say that this is gamma A multiplied by gamma B acting on phi. Okay, so this implies gamma AB is gamma A into gamma B. So gamma is multiplicative, and we have observed that multiplicative maps sends invertible elements into invertible elements. So let us write as a proposition, and we have shown the spectrum is the inclusions between spectrum of the phi of A and the spectrum of A when phi is multiplicative. So let us take, let A be a unital commutative Banach algebra. And gamma from A into C of MA be the Gelfand transform of A. Then we have spectrum of gamma A in this algebra C of MA is contained in spectrum of A with respect to algebra A, and from this we can say that spectral radius of gamma A is less than or equal to spectral radius of A. Okay, so the first one we have already proved in the earlier lecture, and once the first result is true, the spectral radius is nothing but supremum of mod lambda. Lambda is the spectrum of the element. So from that we can say that spectral radius of gamma A is less than or equal to spectral radius of A. And in fact, spectral radius of A is always less than or equal to norm of A. So for A in A, so we have, now gamma A is a continuous function. We have seen that For a continuous function, spectral radius and norm are same. So from this we can say that norm of gamma A is less. So that is norm of gamma A is less than or equal to norm A for every A in A. So that means we can conclude that gamma is a contraction. That is gamma is a contraction. Now we can ask the question, under what condition this inequality becomes equality. That means when is gamma an isometry. So in general gamma need not be isometry. So now let us look at spectrum of gamma A. Okay. So spectrum of gamma A with respect to the algebra. The codomain algebra here is C of MA. C MA is nothing but gamma A is a continuous function on MA. So for any continuous function, spectrum is range of the function. So this is range of gamma A, but this is nothing but gamma A acting on phi, where phi is coming from MA. So this is nothing but phi of A, where phi is coming from MA. Okay. So this is spectrum of gamma A. Okay. Now let us try to look at this inclusion again. Now can we say that this inclusion become equality? So the question is the following. Okay. So we have observed that whenever an element is invertible in A, gamma is also invertible in the codomain. Now suppose A is not invertible. So let A is an element in A which is not invertible. Now then there exists a maximal ideal I such that A is an element of I. But we have already established a one-to-one correspondence between maximal ideals and kernels of multiplicative linear functionals. So there exists a phi naught in MA such that kernel of phi naught is exactly I. Now A is in I, this implies phi naught at A is 0, or we can say that gamma A at phi naught is 0. So from this we can say that gamma A is not invertible. So when A is not invertible in A, we have shown that gamma is not invertible in A. But earlier we have shown that whenever A is invertible in A, gamma A is also invertible in C of MA. So from these two results we can say that A in A is invertible if and only if gamma A is invertible in C of MA. So from this we can conclude that spectrum of A with respect to the algebra A is nothing but spectrum of gamma A with respect to the algebra C MA. Okay. Now from this we can conclude that spectral radius of A is nothing but spectral radius of gamma A, and that is nothing but norm of gamma A. Okay. This is nothing but supreme of mod gamma A phi. Phi is coming from m suffix A. So this is nothing but supreme of phi of A modulus. Okay. So we can find the spectral radius using the multiplicative functionals when we have a commutative unital Banach algebra. I will stop here. In the next lecture, we will discuss about Gelfand map of C-star algebras. There actually we show that there is a one-to-one isometric isomorphism from A into C of M A when A is a unital C-star algebra, unital and commutative C-star algebra. Thank you very much.